Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. Alrighty, so first of all, thank you very much dear viewers for the amazing insights and comments I got on the reinforced concrete retaining wall video. It sparked a lot of discussions and actually is the reason and motivation behind doing this video right now. So in this video, we are going to dive deep into the world of retaining walls using Autodesk Robot. And to do that, I'm going to model me retaining walls, discuss the differences between them, and try to even more accurately model retaining walls. So basically, this video is going to be a deep dive into the world of retaining walls. But before you start watching this, I highly recommend for anybody who did not watch the previous video to watch the simplified version first so that he gets used to the common things I will be referencing from that video and then can enjoy the deep dive with us today. Alright, so to start with, I'm going to select my 3D building design. And today I'm going to revisit the retaining wall design by basically defining me 3 or even 4 retaining walls. So to start with, I'm going to select my grid. Of course, the steps of defining retaining walls and as well as the grids, thicknesses, and all that stuff has been referenced before. For example, dealing with grids and the commands in 3D building design was referenced before in all my videos. For example, beam modeling or plane modeling. The definition of thicknesses for walls and slabs was also covered in previous videos, which are going to be linked above. Now for today, I will define me a longer retaining wall because we are going to take a deeper dive, so I want to be as accurate as possible. So for today, I will define me a retaining wall that has a length of 10 meters in the x-axis. In the y-axis, I'm going to define me only one axis. I will change that in a moment. And in the z-axis, I'm going to define me as 0 and 3 meters, 3 meters being the height of the soil on one side, because retaining walls are going to hold soil from the right side. Alright, so if I hit apply button now, go to my view, I can see that structural grid has been generated, and you can see that this story 1 is basically the story height 4.4. The reason behind this story height is because in story definition the height is set to be 4.4. I have discussed the story definition thing in a previous video. It's also linked above. Feel free to watch this. As for now, I will ignore story 1 completely. Fantastic. Now I promised you actually to model 4 retaining walls, so this is going to be my first retaining wall, and I'm actually going to model me 4 separate retaining walls, so I need to space them out, so I'll just space them by spacings of 10 meters in the y-axis. So I will define me 4 retaining walls like this, and each retaining wall is going to occupy one of those axes. Fantastic. Now, the first retaining wall that I'm going to draw, the first one here, is going to be basically a quick revisit of our previous retaining wall of the basic or simplified video, and we are going to improve upon that. So, of course, I have referenced Braja in Das's book, who basically suggests that the thickness of the retaining wall should be 0.1 of the height with a minimum of 30 or 300 millimeters. And since the retaining wall's height is 3 meters, 0.1 of 3 meters is 300 millimeters. All right, so I'll just say this 300. My thickness is T300 or TH300. I'm sounding like Terminator now. I'll just add that. Yeah, this is a small reference, if you catch that. So I'll add this T300 thing, close, and now I'm able to draw my retaining wall. I just somehow by mistake selected the wall command. I will talk about this command later. I just go back to my floor command and define it as a non-horizontal slab. So I will show you how you can use walls later, but for now I'll just stick to my floor and make it non-horizontal. Alright, so I will just do my rectangle. I will make sure that the local x-axis is the same as the global x-axis by drawing my first line to be in the global x-axis, you can see. So this is the first wall of the retaining walls that I want to discuss. The second wall I want to discuss is going to have the same thickness. The third wall is going to have the same thickness. And the fourth wall is where things are going to change, and I will actually define me a more sophisticated thickness by going to homogeneous. But this time I'm going to not use a, wait, did I use a, it seems I used the wrong thickness, right? Let me just check. Yeah, it seems that I was defining my walls using thickness 250, which is not what I want. So I just quickly fix that by clicking on thicknesses, selecting T300, and then applying that to those panels just in case, because I am somehow thinking that I messed up here. So, well, let's fix that problem very quickly. I mean, I'm a human after all. Alright, so we're continuing with our floors, and this time I'm going to define me a more sophisticated thickness by clicking on this browse button, and this time my thickness is going to vary along a line, meaning I will just basically assume that my retaining wall on top is 300 millimeters according to Braja M. Das's suggestion, and that the retaining wall at the bottom is basically 40 or 400 millimeters, so it's sloped a little bit. To do that, my thickness is going to vary along a line, and point 1 has a coordinate and point 2 has a coordinate with two corresponding thicknesses. Now, the thickness here is 300 millimeters, the thickness here is 400 millimeters. As for point 1, this is my point 1, and for point 2, this is my point 2. And of course, before I start adding, I should change the name here, because otherwise I would be overwriting what I have defined before. So I'll just call this T, I don't know, like 400S or sloped or something. So I'll add that. So after selecting my thickness, making sure I'm not on horizontal slab, I'll draw my basically retaining wall here by clicking those 4 points or 3 points basically, and now I have all my retaining walls drawn. And you can see that the local axis is basically in the global x-axis. I want it to be like this because I want to reduce the amount of confusion I might be facing. Okay, now let's continue with that. And before I continue, I want to see those thicknesses because I want to make sure that this is actually the correct thickness. So if you right click and click display or hit the VV button on your keyboard, you can go to panel and click on panel thickness, and you can see a very cool thickness here. And well, let's take a look very quickly on the right side. That's exactly what I want. You can see that here I have a smaller thickness 300 and here you have a bigger thickness 400. So this is like sloped. For this is constant 300 as we have wanted it to be. Now a quick thing to note here is usually when you design retaining walls, when you slope your retaining wall, it looks usually something like this. Now Autodesk Robot doesn't do that. Autodesk Robot basically uses two horizontal lines like this and slopes the wall on both sides. Now this is an inaccuracy, but there is no way around it. Like, this is how the finite element software works. Now I'm perfectly aware that this is not really equal to what you are doing in real life, but the differences with regard to reinforcement are minimal. So I will just close one eye and say, well, I'm gonna consider that what robot models for me is going to correspond to what is in real life. Reason behind that is because when you design, for example, you want to calculate the vertical steel in the wall, then of course one of the factors that are included in calculating this steel is the moment arm, which is the distance between the concrete compression block and the tensile forces. So like basically this. And this distance is all what matters in designing concrete. So I think that those two are going to approximate each other. So I hope that this little theoretical background could help you understand why I'm going to basically let this one slide. All right, now to continue, now I'm gonna fix all of them and I will revisit this later because there is a lot of nice things I have planned for this wall. So first of all, I'll just click on support, click on fixed, fantastic. All right, so I have fixed my walls, and now of course I can apply my earth pressure again. Now I'm really fast here because I have explained this before. So I just go to define my dead load for reasons explained before. Now I had a nice comment from our dear subscriber Sarpei talking about the British code, which applies a live load, a predetermined live load on the retaining walls. Now this is perfectly fine, and I might be revisiting and addressing this, but for now I'll just consider dead load right now. So when you apply dead load right now and just make a dry run, just perform the analysis. Of course, it will warn you that there are separate structures, but I intentionally have separate structures, so that's okay. So I made a quick dry run. Now if you show the reactions by clicking results, diagrams for members, and clicking on reactions like this, showing all basically, you can see that the wall has reactions that make sense. The reactions on the sides are less than the reactions in the center. Also, you can actually show diagrams for linear supports, because what you see here is the reaction on each node on the support, because if you just hide the support, you can see that the linear support in Robot is modeled by using the equivalent of nodal supports on the line that had that support. Meaning, when you decide that this edge is fixed supported, all the nodes on the edge are going to be fixed supported. So what you see right now is the reaction of each node of those little nodes. Now, Since this is a linear support, what you would expect is not a bunch of loads, but what you expect is actually a diagram for that. So you can go to diagrams for linear support, and if you click on that, you get a diagram that shows you the reaction, which is a little bit better. Of course, you can open descriptions, and you can see the description of those diagrams. And if you remove the diagram, you see the description of the individual forces. Now, if you add those forces together, you will basically get the total reaction. However, if you go to a diagram for linear supports, and click OK, you get something like the average. Of course, you can also, once again, remove this diagram for linear support and check out the support on each and every node of those edges. Fantastic. Back to our point, why is there a force in Z? There is a force in Z because the walls have self-weights. Of course, notice that my reactions are in the global system. You can make it become in the local system, but I will not. So I'll just click on Fx, for example, Fz, for example, or even all. And you can see that the reactions here are only generated because of the own weight of the wall. Now, there is no soil applied, there is nothing, it's just a wall on a fixed support. So let's change that. Let's add some soil. So to do that, I will do it very quickly because this was explained before. So I'll go to special loads and click on soil pressure, and I'll just say that, well, I'm going to define me the soil pressure. Once again, I'm going to have no soil inclination, no wall inclination. My retaining walls are moving away from the soil, and my soil profile is going to be, I don't know, like clay, fine sand, whatever, level 3 meters. Now, one interesting thing is I want to check the difference between robot and what the geotechnical references say. So the friction angle here is 18. So a quick check on Braja Mdas's book. Now, of course, I cannot show you this because of copyright issues, but as I can see from the book that I have in my hands, the Rankine active pressure coefficient is tan square 45 minus phi over 2, where phi is the friction angle. You can see that Autodesk Robot calculates you the earth pressure here, and there is a lot more where I can talk here. It talks about how it's calculated and what is used to calculate the pressure diagram, the inputs here. Now, there is more to this, because you can see that the Autodesk Robot software tells you like what is the active, at stressed, and passive pressure coefficients of that soil, which is nice because you can understand then how the pressure was calculated. So let's try and take a look at what the active pressure coefficient in Robot is versus what a reference like Braja Mdas says. Of course, please notice that the field of geotechnical engineering has a lot of variations in it, has a lot of deviation in it. But let's take a look, and for comparative reasons, let's dive a little bit deeper into this. So according to Braja Mdas, the active soil pressure coefficient is basically tan square of 45 minus phi over 2, where phi is your friction angle. So I'll just try that very quickly on my calculator. I'm getting 0.5278 on the calculator, which is exactly what you see here, which means, yes, Autodesk Robot uses the Rankine, at least for the active, Autodesk Robot uses the Rankine pressure coefficient. Well, since I'm on a roll right now, I'll just check very quickly the at rest pressure coefficient. So give me a second. Yeah, so according to Braja Mdas's book, the at rest pressure coefficient, which is, by the way, taken from a study made by Jackie at 1944, is K naught equals 1 minus sine theta. So let's try that. It's 0.6909. Yeah, so I can only say that the at node is also in line with whatever the reference of Braja Mdas says. I'm not going to check the passive. I leave it for you. I just want to tell you that, well, the soil pressure that you see here is based on the coefficients that were suggested in the reference Foundation Engineering for Braja Mdas. Fine. Now, please notice that there is more details in the reference that I have referenced just before. So feel free to double check that for more details. All right, fantastic. I'm just convinced with the soil pressure. And well, let's apply the soil pressure to all of my panels. So just click on all and hit the apply button. Now you can see that my soil pressures are applied on the retaining walls that I have modeled. So if you run the analysis now, please remember the FZ was 20 here. If you run the analysis now, and basically we just wait, of course, ignore the separate structure, and then go to the reactions again, you can see that after showing the reactions, the FZ is still 20.29. And this is something that was approximated in the simplified video, Because in the simplified video, I simply designed my retaining wall foundation like this. I selected it and designed it. And the design of my retaining wall foundation was based on the reactions that were applied on the wall. And you can see that the vertical reaction on the wall didn't change, although we have added some soil pressure. Now, why is this not 100% accurate? It's not 100% accurate because when you design retaining walls, you rely on the soil pressure on the heel to stabilize the structure, the soil pressure here, and help in improving the bearing capacity characteristics of your foundation. Because if you don't have this pressure, then all the foundation would have is a small weight from the wall, huge horizontal pressures, and some overturning moments, which would cause a soil pressure below it to be like this, or even to uplift maybe. Which is bad because uplifting means that this region of your soil is no longer part of your bearing capacity, which means that your foundation is going to be big. Then that is exactly what happened in my simplified video. Of course, I couldn't dive deep into all those points because, it was the first video. Here, a shout out to our dear subscriber, Donald Khanye. I hope I'm pronouncing his name right, who actually gave me food for thought for this one. If you simply click on the foundation and design the retaining wall, well, you will still get a safe retaining wall, but you are ignoring the weight of the soil on the heel side because you have soil here, basically, the soil that the wall is retaining. And this soil is an important part of the stability of the retaining wall. Now, I didn't do that in the first video because it was like the first video. I cannot just overload you with information, but now is the time to actually dive deep into this. Now, to dive deep into this, there are two options. The first option is a really bad option, which is to calculate the moment from the soil that is applied on the heel side and applying it as a moment on the foundation. Now, I will keep this as my last resort because I want to try something else. But let's keep this in mind that you can theoretically calculate the pressure force and the moment that is corresponding to the soil above the heel and apply it as forces on the foundation when you define your foundation. I just wanted to mention that this is like one of the options that are available, but that should be your last option. The problem with Autodesk Robot is that there is no single retaining wall module, which means that those intricacies are things that you have to keep yourself in mind, and you will have to basically take them into account yourself. Now, my plan for those 4 retaining walls are as follows. The first retaining wall is basically a retaining wall where I will let Autodesk Robot decide the distances and dimensions of the retaining wall himself. The second retaining wall is where I will be using Braja MDAS's recommendation in sizing the retaining wall. The third retaining wall is a retaining wall where I will be using the suggestion from our dear subscriber Sarpei, which is in line with his design practice. I think it's also in line with the British Code. And the fourth retaining wall is the retaining wall where I will personally introduce a foundation and model it myself as a small raft foundation. Now, I didn't cover raft foundations before, so this is like a very small introduction to that topic before I start designing my foundation. For the vertical walls in the retaining walls, I will only show you very quickly how this is designed. I will not go into details because I have explained that before in the video that was about retaining walls simplified. Of course, for the new viewers of this channel, they might be like surprised, like why isn't he designing and explaining the design of those walls? Once again, the reason is because there is another video where I have designed that, and there is no difference between what I've explained last time and what could be explained here. But still, for the ones who still want to very quickly see the design of the walls in this video, we need a combination first, so I'll go to manual combinations. I didn't add live load yet. I might add it later. As a matter of fact, I will just put a placeholder case. Depending on how long this video gets, I might be addressing live loads or not. As I am recording, I really don't know how long this video is going to be. I'm guessing 1 hour, but I could be massively wrong. I have no idea. Go to loads, manual combination, and apply me one manual combination with dead and live. Apply that, hit the new button, and apply me another manual combination where I have my dead load only, which is 1.4 multiplied by the dead load. Okay, fantastic. So now I have my combinations. And to reiterate, The design of those walls has been discussed before. I'm only going to do this very quickly. So to do that, you go to Geometry, Reinforced Concrete Design. You select Slab Required Reinforcement. Well, select your slab. And by the way, you can see that he selected automatically all of them. So I'll keep that. And the question is, what is your load case? Well, you have a lot of load cases here. I think it was case 4. I forgot the case number, so I just have to go back very quickly to check that out. And I'll just run the analysis. And if you calculate, of course, here it asks you to do structure calculations. The reason why it's asking you to do that is because you can see that I haven't calculated my retaining walls yet. So if it calculates, it will remind you that you should redo your structural calculations, which will warn you that you have separate structures, but you're fine with that. And well, you can see that it's done. And if you go to your area of reinforcement, you can see that now you have those nice contour maps that show you the area of reinforcement in the X direction, which is the horizontal direction, and in the Y direction, which is the vertical direction. Strangely enough, if you just click on Y negative, you can see that there is no reinforcement. The reason being is that the retaining walls forces are applied from the right side, and Y negative means bottom. And if you open the local directions, you can see that Y bottom is on the opposite side, which is not loaded. But if you go on Y positive, then everything turns red because everything needs steel. Moving on, I will start designing my foundations. So I just click on right side now and select this foundation only, and basically take this and design provided reinforcement for reinforced concrete elements. When you click that, it will ask you about the load cases, if you want to import the load cases or the load combinations. I want to import the load cases and will let Robot do me my own combinations himself. Of course, there is dead and live, and I've talked about how soil is part of dead loads in ASI code. It depends on your code, so please check that out. I'll basically import me my 2 load cases. Now you have seen that you have here a foundation 1, and since we have defined our raw foundation, if you go back to your geometry, you will see that Autodesk Robot replaced your foundation with a nice wall foundation. Now, of course, the wall foundation's dimensions are totally off charts. It's not correct. That is the reason behind that is, well, we didn't design that yet, so we should wait until we design basically our foundation. All right, so back to our point, I clicked on RC design provided, and I will click on my foundation to access that. So I will not fix anything here. I'll just let Robot do whatever he sees fit. Those options have been explained before. The option of interest for me is, well, I'll just use the concrete, which is concrete 3. No, it's too weak. Maybe concrete 4.5. Longitudinal reinforcement, I'll let Robot decide what reinforcement he wants to use. If I find that the spacing is too much, I might have to intervene myself and select a certain bar size. For transversal reinforcement, the same thing. I will let Robot decide for himself first, and then I might have to change anything I see that needs to be changed. For the reinforcement, I will just leave everything like is. Those options were covered before. Once again, for the loads, Autodesk Robot basically imported the loads that were applied on the foundation. Please notice that N, which is the pressure, which is 22.46 kilonewton per meter. This is the average pressure from dead load from the foundation, and this is basically the wall weight. Now you can add the effect of your heel by adding another force manually and basically applying N for the weight of soil of the heel, and My depending on what the distance of the center of gravity of the heel towards the center of gravity of the wall is. But I will leave it like this, and I will talk about a different possibility to do that. All right, so going to my geotechnical or soil definition, you can see that you can actually define your soil characteristics of your foundation. Now, I will just leave the foundation level to be -0.5, but the foundation has 2 levels, one on the right side and one on the left side. On the right side, I want my soil to be 3 meters above. So you see, I am getting really technical here. That's the reason why I couldn't do this in the first time, because the first time I didn't want to overload you with information. Now I'm applying 3 meters high soil on the right side and applying 0 meters high soil on the left side. Now, if my expectations are correct, Autodesk Robot should calculate the force or the weight of this soil and apply it as load on the foundation. But well, maybe I'm wrong. Let's take a look and see what will happen. The depth of foundation is ½ meter. I'll just leave it like that. You can change it if you want. I'll just leave it because it depends on the site conditions and the planning that you have. Also, notice that I've just used a generic soil. You're responsible, of course, to checking your geotechnical report and defining your soil characteristics based on that report. All right, fantastic. So I can basically close that. Go to my geotechnical options. Here, there is the factor of safety of rotation. It's 1.5. Now, I didn't touch on that last time, but it depends on the code you're using. Maybe your code has a higher factor of safety against rotation, for example, 2.5 or 3. I'm not to judge here. It depends on your own code, and that's the reason why I will just skip it and keep it as is. I think even Braja and Das uses 2.5 or something, but I'll just leave it as is. It's your responsibility to check the code and use it accordingly. Now, there are other points like contact surface and coefficient for contact surface. I will talk about this in a moment if need be. A over 4EX plus A and B over 4EI plus B. The idea behind that is that Autodesk Robot will try to position the column or the wall in such a way that the equivalent force moment system from all the forces is within the central block. This central block is important because it sidesteps possible cases where soil is under tension. Now, I mean, you might remember from your studies in mechanics of materials, Hibla's book, that there is a middle third where the force in the middle third are basically forces that guarantee that there is no tension on the section. Now, I'll just leave it as is. I will not even talk about this. Maybe I would dive deeper into that in the future, but for now, just wanted to tell you what this is about. All right. Now, my soil pressure is going to be 0.3. Now, mind you, this might be a strong soil. It depends on, of course, your region. I mean, for some regions, this 0.3 is a joke because maybe they live in the mountains or something. You might live in countries where your soil is much stronger than that. I have no idea, to be honest, but I'll just leave it as is now. All right, so now I'm going to run the analysis and, well, let's drum roll and see what would happen. So the analysis is complete and, well, let's take a look on what the results are. I'm still surprised. The robot seems to still have a tendency to shift the wall to the exact opposite side. I mean, I've explained that previously, and I just want to show you this. You can see that Autodesk Robot has switched or shifted the foundation slightly to the side of the soil to counteract the soil pressure. Now, this doesn't make sense in a retaining wall context, but well, I don't know, like this is what Autodesk Robot found to be best. So you can see Autodesk Robot has still the tendency to shift the wall on the side of the soil, meaning that it shifts the wall to the side of the soil rather than to the side opposite to the soil. And this time I can tell you why this is happening. It is happening because I'm using a lower value for the overturning factor of safety, meaning that Autodesk Robot deemed it necessary to only include this amount of soil above the heel to resist the rotation tendency of the retaining wall and still have decent amount of reinforcement. I can actually affect the location of the wall by changing the factor of safety of overturning. You can see that stability for rotation is 1.759. You can actually make it different by asking robot to have a higher factor of safety. For example, I'm just guessing, for example, 4. And if you click on OK right now, when you calculate, robot will find out that, well, I need to shift my wall to this side in order for the soil above the heel to resist my rotation. So you can even move it further away by even increasing the rotation factor of safety required to 5, which will indicate to Autodesk Robot that he needs a ton of soil above the heel to cover your factor of safety. You can see that it's actually shifting the wall to the side. So the idea is the position of the wall being shifted to the side, as explained in my previous video, has to do with the factor of safety against overturning. And if you are using smaller factors of safety against overturning, then Autodesk Robot calculates that the soil above the heel is sufficient to resist overturning using this smaller factor of safety. However, if you increase the factor of safety to 5 or 4, for example, of course, this is an arbitrary value. You are responsible for it yourself. You need to check your design code. But if you change the factor of safety, then Autodesk Robot shifts the position of the wall. So this is the first thing I wanted to address. in the design of retaining walls according to Autodesk Robot. Also notice that Robot tries to give you a semi-equalish pressure distribution below the foundation, and that's the reason why it shifts the wall position. The second thing I got was a feedback from our dear subscriber Donald Khanye, who says that, well, the dimensions seem to be off, and he's right, by the way. The dimensions in the first iteration, without all this factor of safety stuff, seemed to be off. The length of the foundation from the side, like this distance, it was too much, and in comparison with Braja Mdas's recommendation, it was totally off the charts, and I agree with him. The reason why this was so was because I wasn't considering the soil above the heel, because I wanted to make a simplified retaining wall. Now let's take a look on our retaining wall after modifying and actually including all the effects that are possible. Well, you can see that A is 3.1 meters. In comparison with Braja Mdas's book, well, he says 0.7h. Now you could think that, well, our robot is incorrect or not accurate, because you would think that the width of the foundation should be 0.7h, which means 3 multiplied by 0.7 is 2.1. And you can see that robot actually is using 3.1. So one first thought that could come to you is, well, robot is oversizing his foundation by 1 full meter. Now, however, this is not really accurate, because according to Braja, your distances are calculated from the top of the foundation, from the top of the retaining wall to the very bottom of your foundation. And if you remember correctly, in Robot, you have defined in the soil characteristics the depth of foundation to be half meter, which means that actually you are going to multiply 3.5, not 3, by 0.7. Now, if you multiply 3.5 by 0.7, you get 2.45. I know this is not really exactly the same as this. I mean, this time the distances are actually much better than last time, because we are including more accurate effects in our calculation. So I think we did a decent job this time in actually modeling as good as possible retaining walls in Autodesk Robot. Once again, I wasn't able to do that in the first video, because in the first video you were still getting to know what retaining walls look like in Autodesk Robot. And you can see the retaining wall has been designed. Now, pardon those little foundations here. You can see that the retaining wall has been designed, and, well, it looks more realistic than the last time. So this now is my first retaining wall. For the second and third retaining walls, I will be very quick right now, and I will use the suggestions by Braja Mdas and by our dear subscriber Sarpei to see the differences of those designs. To do that, well, I'll just basically select my right side like this, select this foundation, and now go to Design Provided. Of course, now I'm going to be very fast because this is a repetition, so I'll just use exactly the same. And this is my foundation now. And for now, I will use Braja Mdas's recommendation to the T. But before that, I need to make sure that everything is the same. Okay, so by the power of video editing, I very quickly matched the inputs between what we have done in the first foundation and what we have done in the second foundations for comparison reasons. Also, I have basically modified my soil exactly like the previous ones. So before I start, of course, I want to use the exact distances suggested by Braja. So I will have to force everything to be fixed. So to do that, I need to basically add me some distances here according to this chart. So, well, let's very quickly do that. Now, of course, you need to try this yourself. For example, H1, which is the height of your foundation. It's going to be 0.3 because 0.1h. And by the way, it's going to be 0.35 because your h is 3.5. 3 meters height of soil and 0.5 depth of foundation. So I'll fix that, and you can see where this is going. So I will quickly video edit this again. So once again, by the magic/power of video editing, I have basically inputted the requirements of Braja Mdas here, and also I have fixed most of the things that could change. So I'll just run the calculation right now and hope for the best. Well, there is a problem. The condition is not met for rotation of the foundation above the y-y axis. The reason behind that is because I have put a ridiculously high factor of safety here to just show you the idea. I'll just leave it as 1.5 and let Robot decide what the actual factor of safety is. So I'll just calculate again. Okay, now it didn't work. Because now Robot has intentionally removed my fixation on the X. It's a torture, I know, but, well, I'm doing this so that you don't have to go through this. All right, so Yeah, I think now I'm ready again. So let's calculate this again with fingers crossed. All right, so it seemed everything worked just fine. I'm eager to go to foundation results. Yeah, what do you know? The stability of, wow, I'm really surprised to be honest. And this is an honest reaction here, because usually when I do those videos, I try to be in the dark intentionally so that you can see my thought process. So I'm really surprised. I'm really smiling right now, because when I check the stability for rotation, it's 3.071, and I think I remember Braja was saying something about 2.5 and 3. So the distances suggested, or the dimensions suggested by Braja, actually give you a factor of safety that is really close. So I'm really surprised. It turns out it worked. All right, so fine. This is the second option that I wanted to discuss, which is using the exact recommendations of Braja MDAS by designing. And the last one I wanted to cover right now is the third one, where I will be using the suggestion from our subscriber in Sarpei. So I'll take this, go to results once again, and go to design once again, provided reinforcement, and rehash the entire cycle. So I just quickly video edit this. All right, so I mean, I'm an assistant professor, so researching and comparison is kind of my thing. So our subscriber in Sarpei has suggested some dimensions. I think it's based on the British standard, not really sure. I'm sorry, I'm more an ACI guy, so I'm really not familiar with the suggestions from other codes, but still, why not check that out? Maybe I'll just pin the designs against each other and, well, let's see for ourselves. All right, so our subscriber says that the base is actually 0.6 multiplied by the wall height, which should be 3.5 by 0.6, 2.1. And he distributes this into 2/3 and 1/3. So the distance here is 1.25 plus 15, 1.4 on one side, and 0.7 on the other side. So exactly as his suggestion. And there was a suggestion about the wall thickness, but I didn't incorporate that. So now also I have made sure that all the settings here are the same. So I run the analysis basically, and well, let's take a look on this suggestion ourselves. So let's run the analysis. Okay, there is a foundation uplift. Let's see why. Foundation results. Okay, there is an uplift here. Not really sure why. I'm just checking. I'm just scanning very quickly. Okay, foundation uplift means that the foundation is going to lose some of its contact surface. This is perfectly fine. The reason why robot is this is perfectly fine, by the way, and we can design that. The reason why robot warns you is because you asked him to warn it. You asked him to actually check your contact surface. So I will remove this contact surface check and rerun the analysis just to free robot from one of the constraints. And now there is no check and it doesn't warn you. My bad. I forgot to fix the eccentricity. So let me quickly do that. Okay, so now I fixed the eccentricity, and let's run the analysis again. I think now it worked. Okay, perfect. And of course, what do you know? It still works. Okay, so we have one design here, which is the design from robots. Robot does it automatically here for you. Robot sizes and by the way, you can toggle between the designs by clicking each of the foundations yourself. So you have the design of robot, which allows robot to freely select everything. You have the design according to Braja MDAS. Now the design of robot actually is using a higher factor of safety for rotation. You have the design for Braja MDAS, which actually obtains a factor of safety of 3 against overturning. And you have the design of the British code, which gives you, I think, a factor of safety of 2 against overturning. Of course, I need you to check the code yourself, to be honest. So which one is the best? Well, factors of safety aside, the best is the cheapest, not including factors of safety here. I'm just ignoring the fact that maybe some of them have different factors of safety. So if you go to Foundation Note and check out the quantity survey to just check what the material was used, well, let's take a look. The total weight of steel is 311 and concrete is 6 almost. So this is the design of British Standard, 6 and 310. Braja is using, let's see, 8, so more, and 394, so more on both sides. But and robot itself, without any guidance, is using 8.3, so similar to Braja. Wait, really? Okay. And weight of 400. So yeah, robot's own design has much higher materials than the design of Braja MDAS and Sarpei. But please notice that I've said factors of safety aside, because, well, look at the foundation of robot, the factor of safety is 4.6 against overturning. In Braja it's 3, and in the British Standard is 2.1, or according to the suggestion to our dear subscriber in Sarpei. So, I mean, yeah, the savings in cost comes at an expense of lower factor of safety. This was a really interesting discussion and really interesting deep dive into the world of retaining walls. The last thing I want to do is I want to very quickly, only quickly, touch on another option to model retaining walls. And this is going to be a very quick touch. I will talk about the details of designing raft foundations later, but for now I'll only tell you how you could model this. Now, first of all, I have used a fixed support for that wall. Now, what I'm going to do is going to be a nightmare, by the way, and it's actually much easier to use those techniques that we have discussed just now rather than using my detailed modeling thing. But I just wanted to discuss this with you just to show you. So, first of all, I will remove the fixed support. There is no support at all now, because I will be drawing the foundation myself. So I'll now draw me a foundation, and I will draw a foundation that has, now of course I need the positions here. Y was at 30, so I'll draw me a foundation that is 3 meters with half a meter on one side and the rest on the other side. So it's going to be 29.5 on one side, and it's 4 meters. So wait, it was 3 meters, I think. So 32.5, I hope I'm not messing it up. On the other side, just add that, apply, close, and now I have some contour, some grids where I can use to draw. Now I'm going to draw me a raft foundation, a foundation using floors. So now I'll click on this thickness here, and I will define me my own foundation. I will call this R300, meaning that it's a raft foundation, but it's not actually a raft foundation. I'm just saying R for raft. This is a small thing I keep doing. 300 millimeters, and this time there are foundation parameters of foundation elasticity. I'm going to model the soil in this slab. Now please notice I will be covering this in painstaking detail, but for now I will just say that there is a elastic foundation, and there are references that tell you what the coefficients of elastic foundations are. I will not do that for now. I will now just very quickly define me a soil. I'll just add me some soil like this, and of course it needs the A and B, or basically the dimensions of the wall. I will say that I have a wall, estimated foundation. This is painstaking detail. I'm only touching on that. I will be revisiting this in the future. So it's a continuous footing. Basically, the dimensions are, I don't know, I think 3 meters and 10 or something. So I'll just click OK. And you can see that it calculated for you the parameters of foundation elasticity. So if you click OK now, or you can actually copy this if you want. If you close that and paste it here, you have your foundation elasticity coefficient. Now I'm going to make me some artificial elasticities here for stability reasons. So I'll just click on add, and now I will draw my, I'll add my thickness first, and now I will draw my slab, so, or my foundation. And I have my slab. I can right click here, click on display, and select thicknesses so that you can see the beauty of this thing that you have drawn. So this is the foundation myself that I've drawn myself. Please notice this is an option that is really advanced, and I will be discussing this in painstaking detail in a raft foundation video in the future. For now, I'm just using robots' automated systems to just get done with it without much of the pain. Now I might be facing instabilities, it depends, I don't know. But I think, yeah, it's still unstable. I thought that. I will be covering this in the future because I want to finish my video below the 1 hour mark. This is one way of modeling retaining walls. There is a lot more detail about this. I will be covering this in a separate raft video, and I might revisit this there again. But for now, I just wanted to tell you that one possible way of modeling your entire retaining wall is to do it like this. I will leave it as is. I will not be diving into this further. I just want to mention that this is a possible way of modeling your retaining wall. However, it's still not accurate because I forgot something in this modeling, and I will not be doing that, by the way. I didn't model the surcharge because there is, besides the soil pressure, there is also the soil weight on the heel. I didn't model that. Now I should be doing this, but I will keep it just as simple as that for now, because the reason why I drew my 4th retaining wall is just to coin to you and spike your interest that you can actually define a foundation using the floor command with soil elasticity. I just showed you this very quickly, and a disclaimer again, it's only a basic video about soil foundation elasticity. I will be going deep into the intricacies of this like I did in this video with soil ranking and stuff in the future, so stay tuned for further videos. Anyway, that's it basically. I hope that this video was beneficial for you and that you liked it. Well, if you liked it, why not thumbs up, comment, share, and subscribe. Especially subscribing, because I'm trying to grow my channel, and subscribing is the best way of helping me grow my channel and increasing my reach. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.